The title of my presentation is a little different from what I had initially proposed. The higher the applied stress amplitude, the higher the stabilized thermal increment. As we know, this is a typical picture we can get from an infrared camera when we apply fatigue loads to a specimen. So this thermal increase is telling us that some energy dissipation or energy conversion is taking place. And this is connected to the intrinsic dissipation. So starting from these experimental observations, we can write the energy balance equation for a material undergoing a fatigue test. We can see on the left-hand side the the time derivative of the temperature, the heat conduction term, and on the right-hand side we see the plastic strain energy rate. We see the stored energy rate. Inside this term we have also the stored energy responsible for fatigue damage. Then we have the heat rate due to thermal elasticity and the contribution of the external heat sources which can supply or subtract some thermal energy. This is a simplified version indeed of the energy balance equation because we are supposing that the coupling heat sources are negligible, so there is not, for example, material phase transformation during fatigue tests, and this is true in many cases, but not all cases. So if we had also microstructure variation phase transformations, we should include additional coupling heat sources. But this is not the case for this presentation. And also we neglect the contribution of any external heat source. So R.E is equal to 0 in this presentation. Now, the intrinsic dissipation, according to the definition given in the literature, is given by the sum of the first two terms on the right-hand side of this equation, namely the plastic strain energy rate minus the stored energy, inside which we have also the terms, the contribution from which the fatigue damage accumulation depends. So the intrinsic dissipation D1 is equal to this term. And in the next slide, we have indicated the intrinsic dissipation as Q dot P because the intrinsic dissipation is related to the plastic deformations. Then we have indicated as Q dot the contribution due to thermal conduction. So by introducing these symbols, we have this simplified version of the energy balance equation. Okay. So on the right-hand side, we have two equivalent power heat sources. The first one is due to plastic strains, and the second one is a reversible equivalent heat sources due to the thermal elasticity. Now, the first strategy to estimate the intrinsic dissipation from thermal measurements during fatigue experiments is called the cooling rate approach. It is based on a very simple technique. First of all, suppose to average all these terms in one loading cycles. This is the meaning of the overbar. So when you start your fatigue tests, you have some average thermal increase and you have the thermoelastic signal, which is superimposed. But if you consider the average quantities inside one loading cycle, you can neglect the thermoelastic variation of the temperature. So if we look to the average thermal increase after a certain number of cycles or after a certain time, we have a stabilized thermal increase, which is quoted here as Ts. Now, if this is true, the first term will disappear because the average thermal increase has stabilized. And so we have that the intrinsic dissipation is dissipated as heat to the surroundings. Now, if you suppose to suddenly stop the test at this time, T star, and you measure the cooling rate after the sudden test stop, you can see that since the thermal field is continuous through the time T star, the cooling gradient is proportional to the heat dissipated before the test was stopped, but the energy dissipated before the test was stopped is equal to the intrinsic dissipation. So the cooling rate multiplied by the material density and the specific heat of the material is the intrinsic dissipation, which was active before the test stop. So this is the first strategy to estimate the intrinsic dissipation. The second strategy is very simple, and we can start from this intuitive observation. If you think to an elastic plastic fatigue experiment with tension and compression strains, so with a stress ratio of -1, you have two temperature shots per cycle. The first thermal shot is when you apply elastic plastic strains in tension, and the second shot is when you reverse the load and apply elastic plastic strains under compression. So if you consider the relation between the intrinsic dissipation and the second harmonic approach, you have the temperature signal varying according to the testing frequency, and you have a second contribution of the thermal signal, which varies at twice the frequency of the applied load. So one could say that the intrinsic dissipation is equal to the second harmonic range of the thermal signal, which is delta T2, multiplied by 2 because you have two thermal shots for each cycles, and then of course you have to multiply by the specific heat and the density of the material. The factor 2 takes into account the fact that the thermal shots occur twice during one loading cycle, but then we need also a parameter beta, which could be strange looking at this formula for the first time. But the reason why beta is needed inside this formula can be understood if we consider the thermal variation in a, for example, virtual experiment. We wrote the equation for the following simple case, which is summarized here. We considered an elastic plastic material obeying a Ramberg-Osgood law. We considered that the plastic strain energy is fully converted into heat. This is not true in general, but it was assumed in this simple virtual experiment. And again, we assumed that the stress state was uniform, and we assumed adiabatic conditions. Now we then simulated a heat extraction in a very simple way just to achieve a stabilized thermal increase. Now, if you look at the harmonics of the temperature signal, you can recognize the first harmonic, which is linked to the thermoelastic phenomenon. And then if you look at the second, fourth, and so on harmonics, you can see that the heat generation due to the plastic strains is distributed in several harmonics, not only the second one. And this is why we need the beta parameter in order to capture the fact that the intrinsic dissipations is distributed in all harmonics, not only the second one. So the range of the second harmonic is not does not fully include the effect of heat dissipation. This is why in the previous formula we needed to introduce a beta parameter which is greater than 1. And we demonstrated that the beta depends on the strain hardening exponent and prime of the material. So with that in mind, we did some experiments in our lab. We considered some round specimens made of stainless steel, a 304 low carbon steel. We applied different strain stress amplitude, starting from 270 up to 405 megapascal. We achieved the stabilization in more or less 10,000 cycles. So we performed 10,000 cycles at the first stress amplitude, then we increased the stress amplitude to the second step, and so on until 405 megapascal. By doing such experiment, we did the following two acquisitions to apply the two strategies. The first acquisition is a steady state acquisition of the temperature signal. Then we did the discrete Fourier transform to analyze the second harmonic of the temperature signal, and then we estimated the intrinsic dissipation with the equation we have discussed before. The second type of acquisition was a sudden test stop just at the end of this steady state stabilized thermal acquisitions, when we acquired the cooling gradient, again to estimate the intrinsic dissipation according to the second strategy. I would like to show you some experimental thermal signals. We have acquired this is a picture reporting two examples of the cooling rate approach. You see that for a relatively low applied stress amplitude, the cooling rate can be measured, but the signal acquired by the infrared camera is affected by a certain noise. The noise, the ratio between the signal and noise is much better if we increase the stress amplitude, just because the thermal increase is higher. So the cooling rate can be recognized in a more clear way. Anyway, after evaluating the cooling rate, we can simply estimate the intrinsic dissipation using the formula we have seen before in the theoretical part. Regarding the second harmonic approach, again, this picture reports two examples at the same stress amplitude, 300 megapascals and 345 megapascal. You see that the range of the second harmonic temperature signal is very small. It is smaller for the smaller applied stress amplitude. It is a little bit higher for the higher applied stress amplitude, but it is a very weak signal. Anyway, by applying the formula with the beta correction parameter we have seen before, we can estimate the intrinsic dissipation. Here you can see some comparisons between the cooling gradient estimations of the intrinsic dissipation and the second harmonic estimation for different specimens, the specimens P9, P10, and P11. As you can see from these pictures, the agreement between the two approaches is better the higher applied stress amplitude, where the thermal signals is much more clear than for the lowest applied stress amplitudes. But in any case, they are in agreement, at least from a certain stress level to the higher stress levels. So after applying these two approaches, the advantages of using the intrinsic dissipation, as I told you at the beginning of my talk, is that you can correlate some well-known fatigue effects, for example, the geometrical effects in fatigue. These two pictures are taken from this paper. We conducted several fatigue tests on notched specimens made of stainless steels, again 304 low carbon steels, which were loaded with a stress ratio, of -1. You can see here different notches with very severe stress gradient effects, with notch radius of 0.5 millimeters up to more blunt notches with a radius of 3 millimeters. And of course, you can see that there is a large scatter of fatigue test results owing to the well-known notch effects in fatigue. So notched specimens have lower fatigue strength than plain specimens, as we all know. This is true if we report the results in terms of nominal stress amplitudes, but if we report the results in terms of intrinsic dissipations versus the number of cycles to failure, you can see that all experimental data nicely collapse into a single scatter band. So this is the advantage of using the intrinsic dissipation approach. So in conclusion, we have seen that two strategies can be defined to estimate the intrinsic dissipation with a rather simple analysis of the thermal signal. The intrinsic dissipation can be used as a fatigue damage parameter, and the intrinsic dissipation proved effective for correlating the geometrical effects in fatigue, at least for the stainless steel material we have subjected to fatigue experiments. So I thank you very much for listening, and I am ready to answer questions now or later on by email or chat. Thank you.